two battery bars.
Okay, yeah, there's just...
Hello, hello. Yeah, there we go. All right, everybody, we're going to get started. Yeah, clap once if you hear me. Clap twice if you hear me. Clap 3 times if you hear me. Hey, everybody. So we're going to get started there. Professor Hug's very nicely writing some things up for me. But at the top, before we start the lesson, I just want to say homework 2's finished now, and homework 3's up. Who found some pretty challenging problems to think about on homework 2? Yeah, so the homework's hard. It requires a lot of thought, especially with how fast we're moving through everything. So yeah, I guess, I'll just reiterate the things I said before. And one I didn't, which is start early. Start early and then work in stages, right? By starting early, all you need to do is just kind of approach each problem once. So again, do it iteratively, work on problems. Each time you work on a problem, it's a new conversation with that problem, and you learn a little bit something new each time. And then the other big thing is work in study groups. If you're having a hard time trying to solo the homework, don't try to solo it. Work with each other. It's not just about being able to help each other, but it's also learning how to communicate math with each other. If you end up in a research area, or even if you don't, being able to talk to each other mathematically is a huge skill, and you only get that from talking to each other. Do you have a question? Yeah.
I was going to ask, realistically, how much harder are the problems on the exam compared to the homework?
Great question. So, that's hard to gauge, but I will say that the hardest problem on the homework is certainly going to be harder than the hardest problem on the exam. The homeworks are meant to, the homeworks in philosophy are meant to help you think through problems, especially since you didn't get enough time to have conversations with them in class. The exams are, the homeworks are where you learn, the exams are where you get tested that you have the understanding of the big picture. So the exams are meant to be easier. They're meant to be doable without knowing the trick. And you may have felt that with the homework. There's kind of a trick sometimes. And sometimes that's why you work in iteration. Work on it once, step away from it. Sometimes your subconscious study group, and you start figuring those things out. Another thing I want to say is kind of how I'm doing this lecture, which is, so these homeworks are created, and then I just sit down and try to grind through them myself. And I'm realizing they are hard. I'm grinding through them. They are hard homeworks. And what I'm trying to do with my lectures is prepare you for the homeworks. I'm not going to hit everything in the notes. I'm not going to hit everything in the discussions. Simply can't. There's too much material. So what I'm going to try to do is get to the things that will be most relevant to you when hitting the homework. Yeah, you could think of my lectures as that way, something that makes reading the notes easier, something that makes reading the notes easier, and when you get to the homework, you will have engaged with some of the mathematical structures already. And I do want to say I've been hearing that a lot of you are showing up to office hours, a lot of you are in study groups, and when I talk to you all about homework problems that you're having problems with, I'm really saying that y'all are working real hard. Like, you're thinking about the problems deeply. And I want to acknowledge that. This class is hard. It moves at a very fast pace, but you're doing good thought. Yeah, you're putting a lot of good thought into it. Yeah, you're learning a lot very, very fast. So who's ready to learn more? We're going to keep up the pace. And today, because I'm trying to hit so many things to get you through the homework, today is going to be a bit of a definitional class. That is, there's a lot of definitions we want to go through, and we're just going to walk through them and make sure we kind of meet each structure that we're dealing with, have a few conversations with it. Maybe there'll be a few things we can prove, but also I'm just really trying to get you through the kind of mountain of definitions that are being thrown at you. Yeah, so I guess let's just start off then. We'll keep this over here. We don't need to read that right now, but this is, like we've been doing, kind of our cheat sheet. It'll be our reference manual as we kind of come into contact with more things as we're going. So warm-up problem, like we usually do. 6 people meet, and they all shake hands. How many handshakes occur? Right. Easily stated question. Meet, hands, how many handshakes occur? You can think of like how many, and also, math is high-powered reasoning with bad drawings, right? So if someone had a guess, what do these dots represent? Yep. These are people. And if we put an edge between them, what does that represent? Yeah. All right. So before we really dive into this, anyone have a guess for how many handshakes occur with 6 people? Yeah. Yeah. 15? All right, so we have 15 here. Who agrees with 15? Yeah, a lot of people. I agree it's 15. Can someone tell me how they see 15 in this picture? Or how they count? How did they count 15? Yeah.
Every man has to handshake 5 other people, so 6 times 5. And we count every shake twice, so it's divided by 2.
Great. So one way to count it is that this person has to shake. It shakes this person's hand, that person, that person, that person, and that person. That's 1, 2, 3, 4, 5 handshakes. And then same with this person. This person has to shake 5 hands. This person, this person, this person, and this person, this person. And then the same for each of them, right? So it's not drawing, but math is high-powered reasoning with bad drawings. So one way we could look at this is there's 5 handshakes for each person, and there's 6 people. And then we said we'd divide by 2. Where does that divide by 2 come from? Yeah.
The fact that each person shakes five other people's hands, but this 5 handshakes, it means that every single person initiates 5 handshakes.
Right.
Which would mean that each person would be shaking hands twice.
Right. So we're double counting some handshakes here. Exactly. This person shakes this person's hand, and they count 5, and this person counts 5 as well, but they share an edge. So this edge is counted twice, once when we count for this person and once when we count for this person. So dividing by 2 just says, look at each possible handshake, all the edges in the graph, but the way we counted them up is by double counting edges, so divide by 2, and that gets us 15. 5 times 3 is 15. Did anyone have a different way of counting 15? Yeah?
So the first person had 5 other people's hands to shake.
Uh-huh. Right. So another way to count this is instead of double counting, just be careful to never double count. Right? So the first person, like before, shakes 5 people's hands. The second person shakes 5 people's hands, but we already counted that one, so don't count that one. It shakes 4 other people's hands. Those are new handshakes. 1, 2, 3, 4. This person certainly shakes 5 people's hands, but these 2 are counted, so it shakes the remaining 1, 2, 3. What's left is 1, 2, and this person shakes 1 person's hand. So, what's that? Exactly. So, this person shakes 5 people's hands. This person shakes the remaining 4, then the remaining 3, then the remaining 2. So this is 5 plus 4 plus 3 plus 2 plus 1. Right? And we've seen this before, right? We've seen that n times n minus 1 over 2 is equal to 1 plus 2 plus all the way up to n. This was the Gauss trick. That's n plus 1, n plus 1. We could count it this way. 5 plus 1 is 6. 4 plus 2 is another 6, and so on. This was that Gauss trick we saw once. So the point is we've seen this problem a number of ways now. We've seen it algebraically with the Gauss trick. We didn't prove it in class, but in the notes, we proved this is true with induction, a different proof technique. And now we can also look at it as a graph. So a big part of math is bouncing back and forth between different lenses and kind of learning a little bit more about the problem each time we do. Right. So 3 different ways we've seen this equation now. Algebraically, induction, and now with graphs. And more generally, we can say, if we have a graph, VE, and, I'll just draw a graph here. We can ask how many handshakes occur here, right? We have a bunch of different nodes, and we can ask how many handshakes occur here. So how many people does this person's hand, how many handshakes happens for this person? Just 2. It's degree, right? We have that terminology now. It's degree. This person? 3. All right, just yell them out for me now. And that one's 3. 3. Right. So now we know the degree of all of these. How well, we could add all these up, right? We could just do 1 plus 1 plus 1 plus 3 plus 3 plus 3 plus 2 plus 4. What do I need to know how many handshakes occurred? Each one of these counts their edges, but each edge participates in that counting twice, 1 on either side. This edge gets counted by this person, and it gets counted by this person. So all we need to do is divide by 2, and this gives us the number of edges in the graph. What is this? This is 3 plus 9, which is 12, plus 2 is 14, plus is 16. 16 divided by 2 is 8. Did I do something wrong, or is that good?
It's 18.
18, thank you. That's part of my pedagogy, messing up, and then you catch me? All right.
And 18 divided by 2 is still 9, not 8.
Yeah. Thank you. So we have 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Great. So we can write this more generally, right? We can say the number of edges is going to be something over 2. What's on top, it's going to be a little bit jargony, but it does say exactly what we did here, right? We're going to sum over the degree of each vertex. That is, for every V in big V, that looks like an R. For every vertex in the set of vertices, we just count up the degree of all of them. We just add them together, divide by 2, and it takes care of double counting. You may have seen this on your discussion section as the handshake lemma, or I think they called it the degree sum lemma, which just says, if you multiply both sides by 2, it says if you sum up the degrees of if you sum up the degrees, that's going to be 2 times the number of edges. Which is just saying, if you add up all the degrees, you're double counting every edge once. You're double counting every edge, right? So this is a pretty powerful thing, right? Like we don't know too much about graphs yet, but this is true of every graph. And when we look at it, it's pretty intuitive, right? Counting the handshakes between nodes, and each edge is double counted. But we're going to be using this throughout the class, throughout today's class. So are there any questions on this to begin with? Okay. So yeah, this is called the handshake lemma, and that's how we kind of introduced it. There's a bunch of handshakes. You double count handshakes. Okay. So that's warm up. Let's start looking at the different types of graphs. There's quite a lot of them. Yeah. Ooh. Yeah. So a lemma is basically like a helper theorem. It's a theorem, like it's a true thing that has been proved, but a lemma is usually used to help bigger theorems, right? Like when you're coding, you sometimes have helper functions. Like to the computer, they're the same thing. It's just a function. Yeah, it's kind of like a subtheorem, exactly. A lemma is this subtheorem that helps the larger theorem. So if you, in your proof you use a lemma, that's why it's a lemma. So this is used everywhere. We use it often. We'll use it today. Great. So let's take a look at types of graphs. The first is complete graphs. All the edges. Has all the edges. I'll just leave that up there and write over here. So what does all the edges mean? It means exactly that with the 6 there. So we could have 5 instead. That's just going to be every edge possible. Everyone shakes everyone's hand. I should have done that the more systematic way, but that works. It's a star in the middle, so that's how I remember. I'm done. So this is called K5. It's the complete graph on 5 nodes. Unambiguous. I give you 5 nodes, connect all nodes to each other, all vertices to each other. That's the complete graph on 5. And you know, we just saw over there will always be n minus 1 times n over 2 edges. Right? It's the handshake problem, really. So if I have 5 cities and I want to connect them with transit, I could certainly do this. I could build infrastructure in between every possible city, and it's super connected. You can get from any place, or places in a city, you could get from any place to another. Why might some people not want this, even though it's super connected? What would be bad about this? Yeah. Expensive. Exactly. Sure, everything's super connected, but that putting subways between, you know, carving tunnels, putting infrastructure, it could be very expensive to do that. You know, or if you could think of them as processors with wires. Like if you have 1,000 nodes, first off, this is the number of edges, and we could say that's approximately n squared. You know, there's a factor of 2 in this sort. You haven't seen asymptotics yet, or big O notation possibly, but it's just saying that the big part here is n times n. That's going to grow big, right? So n squared is the big thing. If you have 1,000 nodes, that means you're going to have on the order of 1 million edges. Or wires, or train tracks, or whatever you have. It's going to be dense. It's going to be a real dense graph, and that can be expensive. So here's another thing. What if instead of, we have our 5 places, we want to get them all connected to each other, but this is too expensive. We could do this. All connected. I can get from any node to any other node. Yeah. Why would this not be the best? Or why would some people not like this one that much? Yeah. Mm-hmm. Yeah, so if you lose just one edge, the whole graph becomes disconnected. Becomes a big problem. Even if it stays in place, if you're starting here and you want to get here, that's a big bummer. You know, maybe it wouldn't be that hard to just put one there, but because you didn't, you're going to have to go all the way around. Like if you're latency amongst processors passing messages, or if you're just trying to hop on a train and get over there, it's just going to be a real pain. So to some degree, a complete graph, this is maximally connected. So this is maximally connected, and a tree, which we haven't defined yet, but that's one of them, is minimally connected. It's still connected, but it's as minimal as you can get it. So we have 3 definitions here, and one thing I didn't put is that they are all equivalent. Let's see, how do I do this? There we go. So these are all equivalent. All of these definitions are exactly the same. What does it mean for 2 definitions to be the same? If I wanted to show 1 and 2 are equivalent, what would I have to prove to show that 1 and 2 are actually the same definition in disguise? Yeah. If and only if, right? So 1 is if and only if 2, as far as definitions go. So that would say that if 1 is ever satisfied, because these are conditions on a graph, and if it satisfies those conditions, it is that type of graph. It's a tree. So if 1 is satisfied, if and only if 2 is satisfied, they're really talking about the same condition, just in a different way. So this can be a little bit annoying. If you wanted to show 1 and 2 and 3 are the same, I think the notes even had a 4th definition. There may be a bunch of different ways you could talk about a tree, but they're really saying the same thing. The problem is that, this is 2 proofs already. That's 2 proofs you have to do, and if you want to do 1 implies 2, 1 if and only if 2, 1 if and only if 3, 2 if and only if 3, there's just a whole bunch of proofs you have to do, especially since you have to do them both ways. This isn't something we're going to do right now, but it is good to know it. If you want to show 1, 2, 3, and maybe 4 are all equivalent, instead of doing if and only if everything, you could show 1 implies 2, 2 implies 3, 3 implies 4, and then make a loop. Show that 4 implies 1. Whenever you can make this sort of loop, you can show all the definitions are actually the same. So for example, 1 implies 2, that's good to show. How do we know 2 implies 1? If we have this sort of structure, how can we say 2 implies 1? Yeah?
2 implies 3 implies 4 implies 1.
Yeah. We can make a train to it, right? 2 implies 3, implies 4, implies 1. So 2 implies 1. So if you ever see a bunch of definitions and someone says, are they equivalent? You get to decide the order of them. Sometimes some things are easier to prove than other, like some directions, or 2 may be easy to show that 3 follows, but if you try to show 1 to 3, it could be a pain. So making this sort of loop, that's always a fun little trick. We're not going to do all of them. Today, we're just going to show 1 implies 2. All right, so let's go ahead and show 1 implies 2. And let's do it up here. All right. So what's 1 again? And let's try to get some intuition for what a tree is, right? A tree says it's connected and acyclic. Acyclic just means there's no cycle, right? This is a cycle. Now we can get from one point back to itself. Cycle, tour, path, walk, those were the definitions we looked at last time. Cycle is when you can take a walk and get back to where you started. So a tree is one that isn't cyclic. Because if you have cyclic, you have redundancy. And when trees are minimally connected, it means all you have to do is delete one edge. Well, we didn't have a tree there. All you have to do is delete one edge and you break everything. And a cyclic is not that. So what definitions do we have up here? Connected and acyclic. Connected and the number of edges is exactly the number of vertices minus 1. And the last one is if you remove any edge, you disconnect the graph. These are 3 different ways to say what a tree is. And you may have seen trees before. Where did I put my... Great. You may have seen trees before, so let's just look at a few examples before we prove anything. I'm going to show you something. Ooh. I think that's all right. So I'm going to just have you tell me whether or not these are trees. right, so first off here, tree or not? Yeah. No. Okay. So this one definitely looks like a tree. Like if you took 61B, this looks like how we think a tree is. There's kind of a root, and it comes down, and you have some leaf nodes. But this is also a tree. Like especially if there was gravity and you picked it up right here, it would just kind of like fall down like a chandelier, and that would look more like that one. And you could do that from any node. That's kind of like rebalancing a tree when you're thinking of it in that sort of way, where there's a root in the sort. But this is a tree. Why is this one not a tree? Cycle, yep. So this is not a tree. And yeah, you know, yeah. We could do more, but the cycle is really visually the thing that's easiest for us to look at. And that's why it's good to have multiple definitions, right? Like sometimes visually it's very easy to see something is a tree or not. There's a cycle or not. But other times it's much easier to argue in a proof that if you remove any edge, you disconnect the graph, or that you're talking about the exact number of edges. So visually, 1 is quite a nice definition. And again, a lot of math is having as many lenses as you can get. So if you can get a bunch of definitions that say they're all equivalent to each other, that means you have a bunch of different definitions to start a proof from. Let me get a better, there we go. Okay, so let's go ahead and, let me just drop that. Let's go ahead and show 1 implies 2. So this is going to be a theorem. Or yeah, let's just say 1 implies 2. What does that mean here? Well, 1 is that it's connected in acyclic. Yeah. So we're just going to assume that. Assume. Actually, let's prove it this way. I'm going to write out what the theorem is so we don't have to keep looking over there, and then we're going to prove this by induction. So theorem, connected and acyclic. I'm just going to put con, and acyclic implies, well, it's, and the number of edges is exactly the number of vertices minus 1. And we're going to prove it by inducting. Well, on what? That's kind of the problem with a lot of these proofs. There's a number of things you can induct with, and there's no real trick to this. Sometimes you induct over the number of vertices. Sometimes you induct over the number of edges. You do have to kind of play around with it. Like, contrary to like how a lot of math is taught in K through 12, where it's like you memorize these things and then you just kind of churn through it. There's a lot of searching and creativity and kind of pondering when you're dealing with proofs. So in this case, I'll just let you know because we don't have time to explore this problem too much. We're going to induct on the number of vertices. Right. So first off, base case. That one's always simple, almost always simple. If we have n equals 1, that's just a point. That's just a point, which means the number of edges is equal to 1 minus 1 is 0. And sure enough, 0 edges. Right. So base case, that one's not too bad. Inductive hypothesis, you know, we're just going to say assume true. Assume for n equals k. And I'm going to go quickly through this last part because we've seen induction quite a bit now. So the inductive step so just about anything we don't understand, we're just going to say, you know, consider connected and acyclic G. And that's what? V and E, always. And we're going to say with the size of V equal to K. And now we can start with that and kind of build something larger. So by inductive hypothesis, its size is K, So that means we have k minus 1 edges by inductive hypothesis. And, you know, again, we can just think, if this is our graph, k minus 1 edges, I can just add one more vertex out here, connected by an edge. And, you know, look at this. Now we have k plus 1 vertices. And we didn't add a cycle. Didn't add cycle. And we only added one edge. Only one edge. So how many edges do we have? We have E equals K, which is the same as V minus 1. Who has some problems with this proof? I went through it quickly. Bells going on. Thoughts? Yeah. Right. So I created a new edge and created a new vertex. Well, the way I created that new vertex is I started with a graph of size k, and by inductive hypothesis, I know something about it, and then I just build up a new vertex, and then can just go from there. Yeah. Yeah, so there's a lot of things it feels like I have to prove. I think a big problem here is there a different color? There is. This part right here. You may have seen this in discussion. If you're going to discussion, this is called the build-up error. We're going to erase all this anyway, so I'm just going to write over that. We can't assume, we can't start with something of size k and then try to build on top of that. The whole point of induction is, I mean, it looks like it, right? It says assume of size k, then we want to show for k plus 1. We're trying to start with k and go to k plus 1. This seems pretty natural. Start with k, go to k plus 1. But do we need this? No, we don't. So this is a thing that should be not clear. This is not how induction is supposed to go. So why don't we do induction how it's supposed to go and then compare, right? So first off, base case. Who agrees the base case is good? Yeah, base case, there's not much problem there. Great. So we leave the base case. Inductive hypothesis, nothing to do there, right? All we're doing is assuming it's. So really, where we mess up is right here. And what we want to do for the inductive step, we'll have them side by side, is, again, we assume it for k, and now we want to take an arbitrary graph of k plus 1 vertices and show for that arbitrary graph it also holds. So we need to consider connected, acyclic, G equals V. But now, with number of edges equals k plus 1. This is the inductive step, right? We don't want to take something that's already good and start growing from there. We want to take an arbitrary graph that has k plus 1 vertices. If we don't start with an arbitrary graph of k plus 1 vertices, we might not be proving anything. So let's look at what we did here. We started a graph that is already k vertices and then say, as by inductive hypothesis, the right number of edges. There's nothing wrong with that. It's just if we start building out from there, what we built works, but it may not be a general graph. There may be other graphs that don't have that property. We need to show it from scratch. Yeah? Thank you. It should be V. Number of vertices is equal to k plus 1. Great. So the only difference so far is that we need to start with an arbitrary graph of k plus 1 vertices and then see what we can do from there. Right? So now the rest follows pretty similarly. It's, you know, this is how we do induction, right? By inductive hypothesis. Oh, yeah, okay. No, so this is the problem. This is why we need to do this. Because now we have a big old graph. And we need to say, this is, you probably had to think about this a lot in the airport problem. Right? It's not that we can start with something good and start growing it from there. We need to start with a graph of k plus 1 vertices, and then say, well, if I take one away, then I have a smaller graph, and that lets me hit it with the inductive hypothesis. But we need to be clever about what we're choosing, because I could just choose a node here, and it might have a bunch of things coming off of it. If I remove that node, I can hit it with the inductive hypothesis. Right? So let's say there's a node here, and let's say I remove it. If I remove it, now I have k vertices, and we can hit it with the inductive hypothesis, but then what? You know, like, because I might add the edges back in. Well, I just don't see the argument here, right? So one thing that does help us with is it at least gives us some intuition. So what if there was a leaf? That is, what if there's one node that only has one edge connected to it? Right. If that's the case, and I remove that edge, remove that vertex and thus that edge, let's see, how do I want to say this? So I want to make a claim real quick, and we may or may not prove this claim. So we may need to suspend disbelief for a moment, but I'm going to claim that, you know, basically every tree connected acyclic implies there's a leaf node. What exactly is in a leaf node? It's that there's a vertex such that degree of V is equal to 1. Any questions about this definition here? This just says that there's a node with one thing, you know, it's basically this, right? Is that there's some node that has nothing coming out of it. And you asked what a lemma was about. Who would feel comfortable suspending disbelief and pretending this was true for a moment and seeing if the proof goes through from there? Okay, great. Great. Here people would love it even. So we'll call that a lemma. If we prove this, this would be a lemma. Right? This is a little helper theorem that helps us prove the bigger theorem. So let's put that lemma up there and finish our proof. So our graph is connected and acyclic. That implies by the lemma, we're pretending it exists. By the lemma, there exists leaf. Right? Yeah, there exists some leaf. That's what the definition of leaf is. Then we can just take it out. we know that there's some such node that looks like that. If we take it out, first off, that doesn't add a cycle or disconnect anything. Right? Doesn't add cycle. You certainly couldn't add a cycle by taking something away, right? Doesn't add a cycle and doesn't, oops, disconnect. Can someone tell me why that doesn't disconnect anything? Yeah. Yeah, it's only connected to one node. Removing that edge would disconnect this vertex if you didn't also take it out, but that's it. And we're taking that vertex out. So what we're left with is an acyclic connected graph. If we have an acyclic connected graph, then, yeah, remaining graph has k minus 1 vertices, k minus 1 edges. I guess that's what I'm writing with the absolute value. So we have k minus 1 edges by inductive hypothesis. Any questions there, right? Because all we've done is we've taken out one vertex, and that lets us hit it with our inductive hypothesis now. Yeah. Because now we have, instead of k plus 1, we only have k vertices left. Inductive hypothesis holds. We can hit it with that. And let's see. And that really concludes the proof. I'm going to put this in a box so this doesn't get in our way. But yeah, if we add it back in, we get E equals k. All we're doing is adding one edge back in. And that gives us, that is v minus 1 since k was equal to k plus 1. So this proof isn't too enlightening itself. The reason we want to go through it is to be really careful of that buildup error, right? We don't start with something that we're OK with and then build from there, because that's only going to build OK things. Even if it works, we're not starting with what we need to prove, which is an arbitrary graph of size k plus 1. Does that make sense? So this is something you may have run into in the airports problem. We just really want to be careful of the buildup error. That's something, yeah. Yes, it has to be the same node that we removed. Because what we're doing is we're saying, this is very similar to the airports problem, is if there's a clever thing you can remove, what you have is a subproblem that you can hit with the inductive hypothesis. Once you have a smaller problem, that's what the inductive hypothesis is for. And now you need to argue, now you need to add it back in and argue that the property still holds. Right? So that's, yeah. Yeah, I guess that's kind of a way to think of the antidote to the buildup error. Instead of starting small and trying to grow from there, you need to start with a general big thing, see if you could shrink down, and then build back up to the original thing and keep the property consistent. Right? So that's really the heart of how you actually do induction as opposed to the buildup error. Yeah? Scenarios. I don't think there's scenarios. There may be things that can fool you easier. Graphs may be one of those things because they're hard to reason about, other than like, you know, you can kind of almost hold them with your hands. You're kind of constructing them, so you take out some nodes, put them back in. It may be easier to fool yourself, but the buildup error is always possible. Really, the thing is you want to take an arbitrary thing of the size you're dealing with, of k plus 1. I think graphs are a little bit more prone to it. It's harder to reason about. And yeah, okay, so let's get moving. So yeah, we're not going to prove this lemma. The lemma, I think, is proved in the notes. That's not too hard. But what I really want to do is get you through kind of these definitions before you get hit with them by the homework. The hypercube, that's usually a scary one for people. It sounds a little bit scary, and then you look at the definition, and it's still scary. So let's go ahead and just give some intuitions for that so we don't get hit over the head with it. So, hypercube. If you have a point, you can make, yeah.
How was the inductive step proved there? If we started with k plus 1, we went to k, and then we came back to k plus 1. Like, isn't it always like more than one more than what we started with?
Yeah, so we started with k plus 1, took away a vertex, and then saw that the subproblem is of size k, so the inductive hypothesis applies to it. The real problem is that once we add it back in, it has to be the same graph. So you can't add a new vertex in with a new edge or the sort. You're just arguing that once you add the vertex back in, now look, I added the same exact graph back, and by using the inductive hypothesis property we have, we can say adding it back in keeps that property. The property in this case being that the number of edges is exactly the number of vertices minus 1. The inductive hypothesis was for k, and then always the inductive step is to show to k plus 1. So by removing that vertex, we can say something about the k size subgraph, and then add it back in and say that property still holds.
So which part of the proof was the initial part of removing vertex in? Because if the inductive hypothesis was just with k, then in which step of the process would we classify the removing of the vertex?
So that's in the inductive step. Because now I just erased it, but we do have a graph of size k plus 1. We argue that there's a special node that's easier for us to remove and put back in, which is a leaf node. And yeah, so in the inductive step, we say like, well, the problem is we have something of k plus 1 nodes, and we have no argument about a graph of k plus 1 nodes. We only have an argument about something of size k. That's the inductive hypothesis. So we need some way to make the graph smaller so the inductive hypothesis applies. And if there's a clever thing, look at the subgraph and say, oh, this applies, and when I put it back, you can still argue the property holds that there is one vertex less than the number of edges, then we're good to go. Okay. If we have a point, any way to make a line from that point. We're talking about the hypercube now. If I have a point, I can just take this point and stretch it. Right? So I can just take this point and stretch it across, and now I have a line. If I have a line, I can take this line and I can stretch it down, and now I have a square. And if I have a square, I can take this and stretch it, or like kind of push it back into the board, and it gives me a cube. So the way we can kind of keep taking an object and stretching it across gives us kind of this doubling of dimensions. So if I take a cube even and I stretch it across the board to get another cube over here, all the vertices kind of get stretched, and then it gets awful to look at. Right? So if you put all the vertices in there, it becomes a complete mess. So we need a better definition of this. But really kind of what a hypercube is you just repeat this process of taking a point, stretching it to become a line, taking the line, stretching it to become a square, taking the square, stretching it to become a cube, and so on. This is how you get into higher and higher dimensions of what a hypercube is. But again, a mess to look at. Once you get to 4 dimensions, because we can't really think in 4 dimensions, we have to kind of just draw it really sloppily on a board. So if we want a better way to think of this, we can label, yeah, okay. We can label what we have. So the line, we can think of this as 0 and 1. And if I want to stretch it now, I'm kind of doubling everything I have here. So let's just say, let's put a 0 in front of this. And now if I stretch it down, I'm still going to have 0 and 1, but now I have 1s in front of it. And now if I want to turn this into a cube, I could put a 0 in front of everything here. And there's a bunch of different ways to stretch it. One way that's a little bit easier to see than a cube is to maybe stretch it inwards, scale it in. This is the same thing as a cube. You can picture it as a cube that's rotated. You're looking into it like you're looking down a hallway almost. Here's the back of the box. You're looking into the front of the box. But it's the same thing as a cube. And now you can have 1s in front of everything. But it's the same thing. 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. What's that?
Is that a tensor?
A tensor. I'm not seeing the matrix here. We can talk about that after class if there's an interpretation of that being a tensor. But when it comes down to it, where is it? Hypercube is right here. When it comes down to it, a hypercube can fully be described this way. Each vertex has an n-bit string, and neighbors are just 1-bit flip away. That fully describes a, so if I have 0, 0, what's 1-bit flip away? Can someone tell me one 2-bit thing that's 1-bit flip away? Yeah. 0, 1 is 1. And the other one can be, yeah.
1, 0.
Yeah, 1, 0. And then something that's 1-bit flip away from this is 0, 0. But the other thing is 1, 1. So these are all 1-bit flip away from each other. Yeah. And the same if you have a, oh yeah, we didn't make that into a hypercube. That would need to be a hypercube, but that's fine. Oh, no, we got this right. And the same if we do this here, we again, all of these get a 0 in front of them now. And we can do the same thing here. These are there's 3 things that are 1-bit flip away from this, because there's only 3 bits, right? And the only other thing other than these 2 is 1, 0, 0. You can fully define a hypercube by just kind of filling in the pieces there. Yeah?
Sorry. Does the number or each bit represent like a x, y, z, or is it just kind of like representing whether at each vertex is flipping? So if you were, instead of going in, you go out, would that still be a 1?
Instead of going in versus out.
Yeah, so at 0, 0, 0, right, you push it into the board, you get 1, 0, 0.
I see. Yeah, so pushing in and pushing out helps us visualize it. But even if I said there was a 3-bit thing, let's say 0, 1, 1. There's going to be 3 things connected to it. Maybe it's nice to visualize it this way, but I know exactly what 3 things are connected to this. Can someone tell me one of them? Yeah. Yeah. Sorry. Yeah. 1, 1, 1, okay. That's 1-bit flip away. All we did was flip that one. What was the other one you had there? 0, 1, 0. And of course, the other one would be 0, 0, 1. So no matter what, it's unambiguous what 3 things are neighbors to this one. It's all the things that are exactly 1-bit flip away. And if we looked at it here, this is 0, 1, 1. Well, there's, 0, 1, 1. If we look at it in this diagram, it's a much nicer diagram to look at it this way than to like just start drawing things willy-nilly. But you could. It'd be the same graph, because it doesn't matter how you arrange the graph. It's always the same. But if we look at this one, there's 0, 0, 1. There's 0, 1, 1. And here would be 1, 1, 1. Right? So it's an unambiguous way to talk about a graph. Or this definition is an unambiguous way to talk about what the hypercube is. And there's a question of why do we care? Like, this is, where does this hypercube come from? It's a little bit out of nowhere. It's a little bit out of left field. And it's a little bit jargony, it feels like. It's kind of hard to picture. Like, you could think of the cube just getting bigger and bigger and then labeling things. But it's a little hard to wrap your head around. So let's, again, have a conversation with this mathematical object and see what we can learn from it. So I'll ask you some questions. First off, how many vertices? Anyone got the answer for that one? Yeah. Yeah. If each edge is labeled by an n-bit string, there's going to be 2 to the n vertices, right? That's just how many different bit positions there are. Okay, another question. How many neighbors for each vertex? Do they all have the same number of neighbors? How many neighbors each vertex? All right. Yeah. N? Okay, each vertex. Right. That's going to be n neighbors for each vertex. Why? Because all of its neighbors are the things that are a bit flip away. How many bits does it have? N. There's only n possible bit flips that could happen. So each one this is a very structured graph. Structure really helps us a lot of the time. So how many neighbors? There's going to be n. We could ask, here's a harder one, but doable. How many edges in the whole thing? So one's a little bit harder, but we kind of know how to approach this, right? So we can talk about this as handshakes, right? There's a bunch of nodes and a bunch of edges. How many hands does this node shake? 3. 3 neighbors. This one? 3. All 3, right? So we know that there are 2 to the n people, 2 to the n vertices. Each one of them shakes n hands. What else do we have to do to this? Divide by 2. Exactly. Divide by 2 because we double counted each edge. So we know exactly how many edges there are. And it's, you could rewrite this as n times 2 to the n minus 1. Same difference. Same thing. One last question. What's our time? Yeah, okay. Another good question is, what is the furthest 2 vertices could be? Think about that for a moment while I write it. What is the furthest 2 vertices could be? As in, you have 2 vertices, and what are the 2 vertices that can be furthest apart? Does anyone have a thought of, the furthest distance? Yeah. So if we have the all 0 string is being claimed that it's the furthest from the all 1 string. Why? Because each edge is a bit flip. It's the longest path to get from one thing to all of the bits being flipped. And what would the length of that path be? That path will always be n distance. To get from the all 0s to the all 1 string, you have to flip every single bit And that takes n edges to get from zeros, all the zeros to all the ones. And that's true of any two things that are all the bit flips of each other. So all zeros and then a 1 is as far as it could be from all ones and then a 0. Right? So yeah, now let's look at 1, 2, 3, 4, 5, 6, 7, 8. Let's say we have 8 cities, and we're trying to, let's erase this. Oh. So let's say we have 8 cities, and we have 3 types of graphs now. We have a complete graph, right? We have a complete graph. How many edges are in a complete graph for 8 cities? We could look at a formula again, but we can also just think through it. Complete graph meaning this is called K8. The K is for Kuratowski, a Polish mathematician. He did a lot of graph stuff. So K8, and the number of edges in a complete graph, well, there's 8 vertices, and they all shake how many hands? 7. Right? They all shake 7, and we double count, so we divide by 2. So that's going to just be 28 edges. That's quite a bit of edges. And what's the furthest any 2 nodes are going to be from each other in a complete graph? 1. Right? They're all connected. All you have to do is go from one to the other. Every, in a complete graph, to get from here to here, we'll just take that path because all of the edges are there. Remember, a complete graph is just all the edges. Okay, so what about a tree? How many edges are in a tree? By definition, and by definitions, there's a useful definition for right now, and that's the number of edges is equal to the number of vertices minus 1. So a lot less infrastructure. If we're trying to put, transit systems between cities, there's only 7 as opposed to 28 edges. But the furthest, this is the problem, the furthest could be 7, right? This could be the case where we have this sort of thing. To get from here to here, you have to go all the way around. And the nice thing about a hypercube is it just kind of sits right in the middle. Where, okay, how many edges do we have? If there's 8 things, that means there's 8 people, and they're shaking how many hands each? Yeah, this one's a little tricky. We need to actually think of what the hypercube looks like when we have 8 things. Yeah, that's going to be 3, because again, the hypercube, when there's 8 things, it's going to be 3 bits. It takes 3 bits to represent 8 numbers. And we're going to have, an actual cube. Not hyper, just a regular old cube. All right. And the furthest this could be, we just said, is a distance of n. So this is 3. So this is really why the hypercube is important. It's something kind of in between a tree and a complete graph, where you could think of, again, bad pictures. We could think of a sense of how connected is a graph, connectivity. And on one end, you have a complete graph being maximally connected, and a tree being minimally connected. And a hypercube is kind of a great middle point that has not too many edges, like a lot less edges than a complete graph, right? Like if there was 2 to the n nodes on a complete graph, that'd be 2 to the n edges. For us, we only have n edges. Yeah. Yeah. Sorry, what's that? Mm-hmm. Keeping me honest today, great. Yes, so there's 8 people, each shake 3 hands, and then we need a not double count. So again, we could always plug into the formula, the degree sum formula, but it's also not too hard to think through, right? Like, how many vertices are there? How many hands do they each shake? Don't double count. Right. Okay, so this is all I want to say on the hypercube. Again, today's a bit of a definitional day. We're kind of running through the definitions because you're going to have to deal with a lot of them on the homework and looking through the notes. The other thing I want to give you so that it's not confusing is something that looks a little bit confusing to begin with. So here's the definition of a bipartite graph. I'm going to throw this up there and take this down. That's the definition of a bipartite graph. Bit jargony. That one's a bit jargony. It might not be the easiest to read. So let's turn it into natural language. We spent a lot of the first part of the semester turning natural language into formal language, but that's not the goal. The goal isn't to take natural language and turn it into formal language. It's to understand something better. And a lot of math is bouncing back and forth in between them. You take natural language, put it into formal language, now you have a definition. You could follow your pencil. Then you get stuck and you need intuition, so you turn it back into natural language. You want to bounce back and forth between natural language and formal language to understand the problem a bit more and more. So let's try to put this into natural language. So, if you don't know what a bipartite graph is, that may look a bit confusing. If you do know what a bipartite graph is, and I have these sets L and R, what natural language word would you want to give to L? Does anyone, what was that? Left, yeah. So we might want to call L be left, and R would then, of course, be right. So all a bipartite graph says is you have your set of vertices V, and you want to be able to break them up into the left and right ones. So you have some vertices on the left and some vertices on the right. And disjoint means that there's no vertex that's in both of them. You're either on the left, you're either on the right. You kind of partition that space. Can someone tell me in natural language what that next part means? That is V equals L union R? Yeah. Right. So V is equal to the union of L and R means that they cover the entire space. There's no other vertices in the graph that are hanging out here. You get all of the vertices in either L or R, and they're not in both. So it's a partition of your graph into something you want to call the left and something you want to call the right. And can someone tell me in natural language the last part, that E is a subset of L cross R? We haven't played with sets that much, so this might be a little jargony. But does anyone have natural language for what this is telling us? Yeah. Yeah, so this is saying that the edges don't go outside of things from L paired with R, right? So basically it's saying that every edge is something from L with something with R. That is, you could take this node and connect it here, and this node to connect it here, but that should not be an edge. That would be something with L from something with L, and that's not what we're allowing. We're only having things that cross the divide from left to right or right to left. No edges between L and L, and no edges between R and R. That's what a bipartite graph is saying. We erase this, and you could have something that looks like this, That's a bipartite graph. You can all the edges are in between them, none amongst the left and right. Yeah?
What would a tripartite graph look like?
You can define a tripartite graph. You would have, S1, S2, S3, and then have them connected. Just don't have any edges amongst S1 or S2 or S3. We're not going to define that here, but multipartite graphs certainly exist. Yeah. It does not matter how many are in L or R. Let's look at a few examples to really clarify it. Because, we can look at definitions all day, But turning things into natural language and turning things into pictures is what really helps us as mathematicians. So I'm going to draw some graphs, and you're going to tell me whether or not they're bipartite. There's one. There's another. And I'm going to do one more here. Okay, let's just go through these. Bipartite? Yeah. Right. Here's an L, here's an R. No edges in between them. Bipartite? No. Should be an R. This is not bipartite. It's complete. There's no way you could separate it because every edge is connected to every other edge. There's no way you could put one thing on, some things on one side and some things on the other, because if you put something on the L side, they're connected to every other thing. They're going to be connected to each other. Problem. Bipartite? Yeah. This is kind of vacuously bipartite. You could put whatever you want on the L and R side, and there's no violation because there's no edges amongst each other. Bipartite? I'm hearing yes, yeah. Here's L, here's R. Bipartite? I'm hearing no's. I'm hearing some arguments here. Okay, so let's look at this one a little bit closer. Let's call it A, B, C, D. This certainly doesn't look like a bipartite graph, right? A lot of good murmuring. Yeah. All right. I'm hearing a lot of murmuring. Let's pull that onto the board. So let's say we have L and R. If I have A on one side, what can't be on the left side if A is on the left side? Yeah. B and D can't be on the left side because it's connected to them. But if we put C on this side and B and D on this side, we actually get A is connected to B and D, and C is connected to D and B. Same graph. So just because something doesn't look bipartite doesn't mean it's not. And that's the tricky thing with graphs, is we abstract away so much that you can just kind of stretch them and twist them however you want, and they're the same graph. So if you're looking for a bipartite graph, you actually have to look for it. You have to say, like, there's this subset of vertices I could call L, and this other subset I could call R, and they actually kind of like do partition the space and are bipartite. So be careful. That's kind of my spiel. Yeah. Are trees bipartite graphs? Are they always? No, I don't think they're always. Could you make them? Interesting question. I don't know offhand. I'm hearing some no's, so there may be some counterexamples you could throw up. I don't know that, yeah. You can kind of think, yeah, so these look a lot like neural nets. You kind of have these interconnections of things. You could think of it as a series of bipartite graphs, yeah, because that's what layers are. The layers don't have edges amongst each other. So you can start like thinking of neural network topologies, and those have graph structure. So graphs are useful in a lot of things. Before we're out, I do want to touch on planarity, because that's going to be on your homework. So real quick, a planar graph, we'll see the definition is right here, in just in natural language. That's maybe not high enough, so I'll bring it here. A planar graph can be drawn on a plane with no edges crossing. Just kind of natural language. And we're just going to ask some things. Is this a planar graph? This right here, planar or not? No. Another trick, looks not planar because look, edges are crossing, but it's not about how it looks, it's about how it can look. So here's the same graph, and it's not planar. Yeah. Now we could look at this. Let's do this. Planar or not? Hard to say. Doesn't look like it. Sure doesn't look like it. But we just saw something that doesn't look like it, and it was.
This one actually cannot.
Yeah, this one actually cannot. I don't think we'll have time to prove that. But that's what a planar graph is. This notion of whether you can or cannot draw it on the plane so that no edges cross. Sometimes you can, but you can't. Sometimes you can, but you can't. One thing I want to say here is when you have something be planar, actually, here's one more. Oops, I didn't mean to do orange, but we have orange now. Planar or not? Yeah, tricky. So it's a cube. Right here you see, oh, it's crossing edges and it's crossing edges there. But again, you could draw it as this thing, where you're looking into the cube like looking down a hallway. But once you have a planar graph, you can talk about faces on a graph. So this is a face, that is, it's an enclosed area. There's another face. There are, in fact, 4 faces. 1, 2, 3, and then outside always counts as a face. That's how we're kind of thinking about it. In this one, we have 1, 2, 3, 4, 5, 6, which makes sense. It's like a die, right? It's a cube. The 6 is kind of what we're looking into in this case. We're like kind of looking into the cube. But we can have these sets of faces here. One wild thing that's proved, again, this is the power of, why are we looking at all these different types of graphs? We're looking at different types of graphs because different things give us structure, and structure lets us say powerful things. So one thing that's said is if you have a connected and planar graph, then it's always the case that V plus F is equal to E minus 2. We're not going to be able to prove that right now. But this is an invariant. No matter what planar graph you have, this will always be true. The number of vertices plus the number of faces will always be equal to the number of edges plus 2. Wild that it's that general, but is always true. We have 3 minutes. So the last thing I want to say, because we don't have time to actually go through it, so the last few minutes here, I just want to give you something for the homework. And if you look through the notes, you can go ahead and prove that E is always less than or equal to 3V minus 6. Right? If I wanted to prove that this is K5, if I wanted to show this wasn't planar by saying, look, it violates this equality, I have a big problem because I don't know what faces look like when I can't even draw it planar. I don't know what faces look like. So a corollary to this, we haven't talked about a corollary. A corollary is a little theorem that follows from a bigger theorem. So a corollary to this theorem is that you can always show that the number of edges will be small. Again, natural language helps us. This is an equation, but what we're saying is not too many edges. We're able to get the number of faces outside of the equation, and if we had time, what we'd prove is that K5, too many edges. K5 has too many edges. It doesn't satisfy this, so K5 is not planar. You could show that there's another thing that's not planar, and yeah. F is the number of faces once you draw a planar graph. And it's these sort of enclosed areas once you draw a planar graph. Here's a face, here's a face, here's a face, and then you have the outside face. Yeah. And yeah, we're done now.